Very good morning to all of you, and special thanks to Infostate and the HP Disaster Management Authority for having me here, and also for the nice hospitality. So I'll be talking about the seismotectonics of the Himalayan region using space geodesy techniques. So the space geodesy has two major components like the GPS and the interferometric synthetic aperture radar, or the INSA. And I'll be talking about how we can use the space geodesy to understand the earthquakes and the tectonics of the Himalaya. And I'll be talking slightly with special reference to the western northwestern region, especially the Himachal region as well. So next please. So I'll start the talk with a brief introduction to the earthquake cycle and the space geodesy technique what we are going to use, and two earthquakes where we study using the space geodesy, the 2015 Nepal and the 2019 Manipur earthquake, and the interseismic strain rate and the seismic coupling in the northwestern Himalaya. And finally, I will give a brief introduction to the NICER mission that will be launched next year. So earthquake cycle is a very fundamental theory and very important theory. As we all know that earthquake is a sudden phenomenon, but there is a preparatory phase of before the earthquake. So here the graph shows how along a fault how the strain is accumulated over years. So there is a slow strain accumulation, so that's called the interseismic phase, where few millimeter per year strain is getting accumulated, and when it exceeds the frictional strength of the fault, it leads to an earthquake. So the slow strain will, whatever accumulated will be released in a moment, giving a large slip of few meters magnitude, and so that's called the post-seismic phase. And after that, there is a relaxation, that's called the post-seismic phase. So in order to understand the earthquake dynamics, it's really important to measure the three phases of earthquake cycle: the interseismic, post-seismic, and post-seismic. And where geodesy has a major role, how we can measure these earthquake phases to understand the basic physics of the earthquakes. So in space geodesy, the GPS is a well-established field, so I don't want to dwell more on that. So as we know, the geodetic GPS can measure the millimeter scale deformation. So whatever causes happen within the earth on the fault is manifested on the surface as deformation, and GPS can measure the deformation, and it can probe the three phases of earthquake: the interseismic, post-seismic, and post-seismic. So you can clearly see a graph here showing the three component deformation that was established. Okay, yeah. ठीक है, कोई बात ना problem. So ये also yes. Okay, I'll continue. So this graph shows the slow interseismic phase, the strain accumulation, and you can see almost 1 meter deformation during the 2015 Nepal earthquake and the post-seismic phase. So this is one example of how we can use the GPS to measure that. And the bottom figure shows the global distribution of the GPS network, and as you can see over the Asian region, especially over the India, the open source GPS networks are very less, but it's very high in the Western US and Japan and countries like that. And it's really important to have dense GPS network in order to precisely measure what kind of strain is accumulating over the plate boundaries. So an alternative technique is the interferometric synthetic aperture radar. This is a relatively new field where we can measure the strain over a large region. GPS is a point-based measurements. Here you have a synthetic aperture radar. It's an image of typically a few 100-kilometer length and breadth. And if you process the image using a technique called interferometry, and interferometric technique works, it's a very basic principle, works on the Young's double slit experiment that's shown on the left. That you can clearly see there is one light source split into two. Now on a screen you can get the interferometric fringes. And it's important that the amplitude of the fringe depends on the distance between S1 and S2, and the phase, basically the fringe pattern indicate the phase. One phase cycle is the 2 pi, something like that. So this is a basic principle, and INSAR works on the same principle. So if I put the system upside down, the two sensors at the top, those are the two SAR sensors, SAR1 and SAR2. Typically it's a one sensor, it revisits after a few days, so you get another measurement. And it is sensitive to the topography and the change in topography. So SAR can measure the topography in terms of few millimeters of accuracy, but it can precisely measure the change in topography due to an earthquake or any other geological process, like if even in the centimeter or even millimeter scale, it can measure. So that's the beauty of this technique. At an altitude of 800 kilometers, the SAR sensor is there. It can measure the deformation on the surface of the earth with few millimeter accuracy, covering large area. So this is an alternative technology. So there are many geophysical applications for the INSAR. Few applications that we have done, there are many others. I just shown here, not going into details. So during an earthquake, the primary, there could be secondary ruptures and primary ruptures. Even INSAR could be used to map some of the secondary ruptures during the 2021 Assam earthquake, because it's a deep earthquake and there is no signature on the surface for the primary rupture. Or even you can use it for measuring the deformation caused by, the subtle deformation caused by an earthquake storm, that's in the Polgar storm, or over a volcano. So a volcano can deform either due to the subsidence of the lava field or due to the magma changer, the pressure change in the magma chamber. So here again, in fact, this is the mean deformation over a period of time. So, and the right side map shows with time how the deformation changes at one point because of the changes in the magma pressure. And like that, so these are all basically tectonic deformations, and you can use it for non-tectonic as well, especially, so here is a case of the Terry Reservoir where the seasonal water level change can cause minute deformation that we can use, or even groundwater. It's a very non-phenomena. Groundwater overexploitation for subsidence, and even for a nuclear test, it can produce large ground deformation that we can detect. And all these are measurements, and we use suite of geophysical models to understand the physics behind, or physical process behind all these different phenomena. Now coming to the Himalayan part, yesterday many people have already explained, as we all know that Himalaya is a result of the Indo-Eurasian convergence, and the plate velocity is almost 4.5 centimeters per year, and half of that is accommodated over the plate boundary. So if you have a south to north section, so you can see the convergence of the Indian plate beneath the Eurasian plate, and the seismicity is plotted here. So one interesting thing is that most of the seismicity is clustered around a steep ramp that is almost 100 kilometers away from the main frontal thrust. And there are two kinds of earthquakes. Most of the earthquake happens or originate at the main Himalayan thrust, near to the ram. And there are two kinds of earthquake. The great magnitude earthquake, which can originate at the ram and travel all the way up to MRT, causing the rupture of the MRT. We have very few events. There are historical events, but the 1950 and 1934 are well-known examples of that. So the rest of the events are 6+ magnitude earthquake, which are typically called the blind thrust or sometimes out of sequence thrust, but these are basically partial rupture. That means whatever the strain energy is accumulated, only a fraction of that is released, and it's a very interesting question whether this can act as a catalyst for generating a great magnitude earthquake. So this is a case of 2015 Nepal earthquake. So here an interferogram is shown which measured the deformation caused by the earthquake, that is almost 1 meter along the line of sight, and there is an aftershock also after a few days that is also measured. And during the post-seismic period, which is a short-term post-seismic deformation, the deformation is shown here that is just opposite to the post-seismic deformation, so which suggests a typical afterslip on the fall. So here is the model. So we model the slip on the fall, considering the flat ram geometry of the main Himalayan crust. So what we can see, almost a 6-meter slip was caused, and the 3D image shows the deformation draped over the topography, and subsurface you can see the fault plane with the slip values. And the important aspect is that how the rupture propagated, because even in terms of earthquake hazard, you can see that the epicenter is almost 150 kilometers away from the region of maximum deformation. So we expect maximum hazard, maximum issues where the deformation is maximum. That is not correlated with the region of epicenter. So it's a kind of runaway rupture that is captured by the INSAR. And there are interesting questions why this unilateral rupture propagation happened and so. So I'll come to that. So in the post-seismic period, most of the deformation is, or the slip is the model, is north of the post-seismic rupture. Typically it's a seismic afterslip. And we took long-term data, 2015 to 20 data, against the recent result, which shows that most of the afterslip is again towards north, and towards south there is no seismic slip. That means whatever stress is accumulated in the south is not yet released. That's important in terms of earthquake hazard assessment. And the rightmost graph shows the logarithmic fit, how the post-seismic period, how the deformation varies. So this is the second case of the Mirpur earthquake. So this is not a typical Himalayan earthquake where the deep ram rupture occurred, because this earthquake occurred very close to the main frontal crust, and it's almost a 6 magnitude earthquake. So the interferogram shows about 12 centimeter deformation along the line of sight. And again, the geology and the rheology of this region is slightly different from the eastern side of the Himalaya. I'm not going to the details. So that's the interesting part, why a 6 magnitude earthquake can occur a completely locked frontal part of the Himalaya. So here is the slip model. So we use a Gaussian inversion to deduce the slip parameters. So an interesting observation is the comparison between the seismically or the teleseismically constrained source parameters, the magnitude, depth and peak, and the geodectically constrained one. There is a difference, because the INSAR can give you the near field deformation, so that has better control over the depth. So this earthquake is very, very shallow. It's about 5 kilometers on a 2.5 degree dip on a very shallow portion. So here is a cross section which shows that it is just at the foot of the frontal ram the slip occurred. And here is the Coulomb stress change that shows that the earthquake has increased the stress in both the directions. And in the afterslip model is again interestingly, the afterslip is mostly towards south. That is just opposite to what we observe in the Nepal case. So that clearly says that whatever stress has released, again, there is a slow aseismic upper slip towards north of the rupture. Yeah, coming to the interseismic deformation. So this is for the central Himalaya, part of the Nepal, then some Indian region as well. So this is a compilation of the GPS data which gives you the horizontal velocity for almost 20 years data. So we can see again the main frontal thrust, the velocity is very less, it is log, and going towards Tibet the velocity increases. And we have insert sections at few places. So there are two sections like the NV-SAT and the LOs, which primarily detect the vertical deformation. So we can see that there are 5 to 8 millimeter per year vertical, that is the actual growth of the Himalaya in that region. And here is a model, a 2D model from a long south to north section, and which shows how the continental collision happens and where the slip is accommodated. Now, whatever measured slip, we invert for the interseismic coupling. So interseismic coupling is nothing but the degree of locking of a fault. That is really important for earthquake hazard assessment. So the red region shows it's completely locked, and the blue region shows it is aseismic creep is happening. So in the subsurface also we can see from M of T to down to depth of 20 kilometers, the fault is completely locked. And after that, there is a relaxation or the creeping is happening. So the transition is very important from the locked portion to the creeping portion, where maximum the Himalayan seismicity originates. And also it should be noted that most of the spatially, the creeping or the locking pattern is somewhat uniform along the arc. So this is the strain and the seismic B value we compared. Both the measurements are before the 2015 earthquake. And it's interesting to know two strain patches, one towards west of the 2015 Nepal earthquake and one towards east. And in the same, the seismic B value also shows the high stress region in the similar region, and one of that asperity has been ruptured during the 2015 earthquake, but the western asperity is yet to be visited by an earthquake. So that's the way we can say, considering the dimensions of the asperity and the past earthquakes, so we estimate that the western asperity could produce an earthquake of magnitude 7.6 or so. And again, it's very important that the 2015 is a partial rupture, whether it can fuel an 8 plus magnitude, because there is a theory that a series of partial rupture can fuel a large magnitude or great magnitude earthquake. So again, this interseismic coupling pattern spatially, how does it vary? There are two schools of thought. One is the uniform, even we propose that, and there is a recent paper which shows that it varies spatially. There are low coupling and high coupling patches. That is also again important, because the rupture propagation depends on the spatial pattern, how the spatial, the highly locked portions could be released and rupture could be, there could be a break in the rupture with the low coupling patches. So in order to understand whether it is due to some data gap or the modeling problem, we took a new GPS data from the Himalayan seismic gap in a collaboration with IIT Bombay, and this work is just recently communicated, and which shows that the new data in there were data gaps, and we did again the interseismic coupling model, which shows that the coupling is more or less uniform. Even if you do it with more data, there is less variation, or there is no drastic spatial variation But there are some interesting aspects like, and here is the strain and here is the seismic coupling. If you see the Himachal region, there is a wider locking zone compared to the eastern region, and there is a seismicity gap also in that region. So there could be some inelastic mechanism. So that need to be confirmed with further analysis. So now the question in the Himachal or the seismic gap region, what could be the next earthquake, or what could be the possibility of the earthquake? So from the strain rate we can estimate the seismic moment of the region considering the past earthquakes, because the past great magnitude earthquake happened in at least 500 or 700 years back, and this calculation shows that, So this calculation shows that this seismic gap region could host an earthquake anything more than 8.5 or so. Okay. Okay.
Can you go back to the previous slide?
Yeah, sure.
I think most of us are interested in this.
Sorry?
We are interested in this slide.
Yeah.
So please explain it.
Okay. So the question is, once a 8+ magnitude earthquake happens, then it takes a long time to go for another earthquake. So we need to look at the past earthquake when the last time there was a 8 magnitude earthquake which ruptured the frontal portion. So that is around 500 or 700 years. And using the